Namaste, everybody. So can equations be descriptions of self-evident mathematical truth? Traditionally, an equation is a true statement, but we don't prioritize the apprehension of that equation in its totality. Usually, equations are considered useful utilities through which we can derive answers to relevant questions. But if an equation can become something that we can hold in our mind and, in a sense, read in the fabric of existence, then it has a spiritual relevance. We become the form of that which we direct our attention to. But a superficial arrangement of symbols is not enough to apprehend the nature of the abstract truth that those symbols refer to. So today's equation is the equation for the slant area of a cone. Can we see this equation directly? Now, it doesn't have to be the equation in the traditional sense as if you were to look it up. It may be written in your own way, a way that implies within it the nature of your apprehension of the equation. So there's another traditional approach that society currently has, which is to simplify equations down as much as possible, whatever that might mean. Sometimes it means just less symbols or write it in the conventional way, but that's not necessary either. We can write equations in ways that aren't necessarily as simple or as conventional, and they would simply emphasize a particular aspect of the way in which we are apprehending that abstract truth. So pi r squared is a very common. Tau over 2r squared is less common. 1/2 circumference times radius is even less common. I'm looking at different ones, just I'm seeing what they might be. Better not to memorize. I didn't memorize 1/2 circumference times radius. I just closed my eyes and read out of the fabric of dimensionality that equation, which is not one that almost anybody memorizes. Conventionally, we would say the circumference has a radius in it, so we have to not use the circumference, right? But why? What if that's the way you're seeing it? And what if you're in a situation that's from the spiritual perspective, but from a practical perspective, in terms of a practical application, not that spirituality isn't practical, it's the most practical thing, right? Because life is based on experience and you're the filter through which all experience comes through. The most practical thing to do is to make yourself a beautiful spiritual apprehension of the universe. This is practical. uh, but to use the more conventional use of the term practical, if we have some sort of utilitarian application of the equation, perhaps we know the circumference and the radius, and therefore 1/2 circumference times radius is very easy, right? There's a constant ratio between the circumference and the radius. So if you know the circumference, you can rewrite it as tau times r, right? So tau times r, so 1/2 circumference times radius would be 1/2 tau times r, which would be 1/2 tau r squared, which would be the other way to look at it, which would be pi r squared as well, because 1/2 tau is actually pi. But you see, there's a lot of subjectivity. This is the point I'm trying to make. There's a lot of subjectivity here. When somebody chose tau instead of pi or pi instead of tau, they made a subjective judgment call, did they not? So where is the purity of math? Well, it's got to be in your own heart, because as long as there's some subjective aspect, that subjective aspect must be aligned with your heart. That's what makes it pure. And also to recognize that that is a subjective aspect and not an objective aspect. Perhaps there's a way to see the mathematical truth without naming it, and then therefore doing so, avoiding all subjective orientations. Subjective, by the way, means pertaining to the subject, pertaining to the observer. Objective means pertaining to the observed, the object, unrelated to the observer. Important words in the spiritual path to recognize what is of your consciousness and what is of the suchness of things. Anybody want to message Jacob and let him know he's sleeping in or whatever he's doing? Robert, would you mind messaging him? Tell him the bell went off. You sense it? Nice. So the area of a cone, the slant area, not the base area, because it has a circle in it, right? But the area around, what is that area? Now let's not look it up. And if you have it memorized, put that out of your mind. See if you can, a funny thing to say, right? If you have it memorized, put it out of your mind, right? So see if you can, let's take a few minutes, take some space and think about what that is. I would be very pleased if somebody came up with something completely unlike anything I'd ever thought of or seen before. That would be cool. Possible. How would you describe it in your own symbols, in your own words, in your own way, or a way that's your own? So if you're having trouble getting started, you might start by considering some of the properties of a cone. How wide is it? How tall is it? How slanty is it? What's the angle? Whatever you want. Like, you have to start with some sort of properties. right? The equation is determined, or the slant area is determined by certain properties of the cone. It's a relationship. The area is one property. There's other properties, and you can have a relevant relationship between different properties. Now, definitely don't rush. It's okay to just meditate first for a moment. Mm. Mm. Anybody coming up with anything? In the future, if you see on the calendar an equation, you can spend the week beforehand contemplating it and see if you could be prepared in that way. Because you could think about it for an hour and then the class will be over. So I'll show some things now. You might have seen it already, though.
I I am not able to find the relation between arc length and angle made.
Of a cone? Can you explain more?
So the arc length and the angle made on the top, on the center of the circle. Yes,
Oh, nice. So you're thinking of this angle.
yes.
Okay.
If, if there is a way to relate these two, then no, not this. When this expands,
Okay.
when we open it up.
Okay. Okay. So Karan has an insight here. You can take this and you can cut it on one of the edges. And when you
And
do
spread.
that, you get this sort of thing.
Yes,
Right?
that base is now 2 pi r.
And then there's an angle here. Oh, and you want to know the arc length, which is this.
That arc length might be 2 pi r. The
2 pi r, where this is r, right?
yes,
Okay. And I'm not going to use 2 pi r because the more relevant constant in my poetic subjective insight,
Oh,
tau. So this would be tau times r, right? Or 2 pi times r. So that's the arc length, which actually came from this length. This length is this length. Robert, what do you think?
now
I want to make sure. Robert, do you see that?
Yes, yeah. I was trying to envision opening it, but I couldn't like how would you just come up with an equation to actually create area? It's hard. I remember teaching this for years in high school, and it was always like, is it the slant length? Is it the height? The kids just always got so confused with this specific one, So
Yeah, because they get
I don't know, if I was
based on memorization, you get very confused. That's the thing about memorization. You get very confused, which, I mean, they're like, well, is it L or is it H? Or like what? But that's because they have no way to remember it, right? Like some visceral experience through which they could remember it. So if that is the distance around, let's just relate some of these things. This length is this length. Now, here's an interesting question to ask. Is this a part of a circle? Or is it maybe, why would it be part of a circle? Maybe it's not, Quran called it an arc length, which implies that it's part of a circle. But why? Is it really a part of a circle? So we have to actually confirm this aspect of the abstraction.
nice.
Mhm. It's very tempted to be like, oh, of course it's part of a circle, but why? Why is it a part of a circle? Ayush, you want to try?
Because can I say?
Okay.
Because the distance from that, if we consider the uh, intersection point a center of a circle, then yes, then this arc is at equidistance.
Okay. So
So we can call
each of these points
mm,
is the same distance from this central point, which means that it's a part of a circle, right? Because
yes.
each of these is the same distance from that central point. Okay. Okay, cool. So if that's the case, there's a big circle here. Okay, I want to let you guys have a few minutes and see if you can come up with the equation now. And really check that voice inside your head that's competitive and judgmental of yourself. You be like one of those children who is discovering math for the first time. You know what they look like, how they are. There's no judgment. They don't have all that extra stuff that you develop in elementary school, basically, right? Starts young. Uh, certainly as an adult, you've decided if you're good at math or not and how good you are. All of that there's no place for that, right? Baggage. Just enjoy it. It's for you. self-love. So anybody have any insights they want to share other than crayon first? Okay. So this is L. Right, the green line is L. L is the symbol for slant height. Why is it called L? Let's call it S. Slant height. You see, it's really important not to just follow conventions. You can follow conventions when you're in a situation where it's conventional. And if you don't follow conventions, you just confuse people. But when you're in your own privacy, maybe don't follow conventions unless you want to. Just the point is to recognize that you don't have to, right? You can, or you maybe you should, maybe you shouldn't. Make sure that's coming from inside of you, though, that decision. That's what I'm saying. So if this is S, what's the length of the yellow line? Well, tau times S. Right? Because S is our new radius. In fact, you know what I like better than S? It's kind of like a big R.
Yes.
Yeah, so it's tau times big R. Okay, so what percentage or fraction of the circle is filled in, basically? Well, it would be tau times little r divided by tau times big R. You see that? How do I know this? Because how do I know this? Because this length, the red line divided by the yellow line corresponds to the number of very thin pizza slices, right? Let's say the yellow line has a length of 1 and the red line has or let's say the yellow line has a length of 100 and the red line has a length of, I don't know, something smaller than 100. We can see that for every unit of length, there's a corresponding unit of area, proportional area. If you double the arc length, you double the sector area. You see, even something like that, do you see how this is a very self-evident thing? If you double the arc length, you double the sector area. Wait, am I right about that? Double the arc length. Yeah. You know why I'm hesitating is because usually when we increase the length, we increase the area proportionate to the square of the length we've increased it, right? So, but in this case, why is that different here? It's different because we're increasing, we're not increasing the radius, right? So if you have a rectangle and you make the rectangle taller but not wider, you see what I mean? If you take a rectangle and you make it taller by a certain amount but not wider, you're actually increasing the area proportionately to the height. And because these are, even though these are triangles, it's the same situation because we're keeping R the same no matter what. We're just changing the sector, sector area versus the arc length. We're increasing arc length. So in that case, we can say that the length of the red line divided by the length of the yellow line would be the percentage or the fraction of the area that the slant height is of this big circle.
Why not square of the radius?
Can you make a full, complete statement? Why not? Why the square of the complete
You are
radius?
taking the ratio of tau small r over tau capital R. Why not?
Okay, so this is so let me tell you what I'm going to use this for. That is a fraction, right? If we multiply this by the area of the yellow circle, we'll get the area of the green part. See that? So the area of the green part is a fraction of the area of the yellow circle, right? Is Karan, are you saying no?
Yes, I'm saying it is correct.
Oh, that was an Indian yes. Right? No, he's like no. Yes, this means no. This means yes. Okay, good. So, and now the area of the yellow circle, we can just go ahead and call it for now pi capital R squared. So, and then this becomes tau R over tau R. And if we multiply this out, we get R over R times this, which is pi R R. And the convention is, I believe, pi LR or pi RL. I want to make sure everybody sees this. Robert, let's talk about it.
Yeah, I mean, it's still a tough equation, but yeah, it's tough to visualize when things are curved because they're not as like cut and dry. I like how you broke it down though, with the ratio of the tau little r over tau r.
Mm-hmm.
That was the step that I was missing in my head to try to put this together by myself.
So
Just think about
so you can see, isn't that interesting? The little radius to the slant height, which is the big radius, is actually the factor that determines what fraction it is of that big circle. But you know what's interesting? Now that we see this, there's an even more obvious hint. So I'm going to erase it in a moment. So I just want to make sure everybody sees it. Ayushi, what do you think?
Yeah, I just remembered that the curved surface area of a cone is pi RL, but now this is a like very new thing for me that you can open up it and then you have a new radius and then you have a circumference and then you can correlate the sector with the whole circle and then come up with the same equation. So I'm
Nice.
wondering.
Nice. Beautiful. Okay, so you're following it. Now, is this...
I want to add something, Adam, please.
Yes, please. Yeah, go for it.
Why do you take the ratio of circumference? Why not the ratio of area there?
Can you say it again?
Why don't we take the ratio of area? Why are we taking the ratio of circumference?
Oh, well, do you see that the circumference and the area are proportionate? So if we increase, or let's say arc length and area. So is there a proportionality between the arc length, and that means proportional, and the sector area? Arc length and sector area, there's a proportionality. This is maybe a little bit of a jump. It means if you increase the sector area by a certain percentage, you increase the arc length by a certain percentage, and vice versa. Is that a yes?
Yes.
That's a yes.
Yes.
Okay, okay. So, okay. He's like, so good. It's like when you have a good bite of food.
I'm just enjoying this.
What was that?
So
You must
I'm
have.
just enjoying. So
I love that. That's a good
and
one.
my guess.
Okay, good. So I'm going to erase this because I want to show you something now. Here's another thing we can show you. Now there's another way to look at this, now that we see it a little differently. This is our cone unraveled, okay? So this length is tau r, right? And this length is the slant height, capital R. Now, each of these is an actual triangle, not warped space. And this is very important to recognize. There's something called Gaussian curvature. Has anybody heard of Gaussian curvature? Have you heard of a developable surface? These are some interesting terms. You can't turn a sphere into a flat piece of paper. Why? Because it has positive Gaussian curvature. You can't turn hyperbolic surface into a piece of paper. But you can turn a cylinder into a piece of paper. You can turn a cone into a piece of paper. These are called developable surfaces. And when the Gaussian curvature is 0, as it is in the case of a cone and a cylinder, it can be flattened into a page, into a plane, which also has a Gaussian curvature of 0. But if the Gaussian curvature is positive or negative, you can't do that. So I'm just pointing out that there's this is a part of. Now, did you ever think that when you're working with your 8th grade or 9th grade students, or 10th grade, who knows what grade, that look at all the dimensions of contemplation here. That's related to Gaussian curvature and developable surface. It's related to proportionality, right? There's a lot here. Well, why do we have to quickly memorize the equation and see if we can use it? I don't think that's the full lesson that God had intended for the slant area of a cone, right? I mean, if every beautiful, relevant mathematical equation is a thought of God, as Srinivasa Ramanujan said, then there's a lesson in each one, right? To come to know the nature of the dimensional abstractions that is our own mind. So this is a bunch of triangles. That's my point. If this is a bunch of triangles, right? Let's say we need an infinite number of these, right? Okay, so calculus term, right? It's also calculus. Just saying, there's a lot here you can go into. So if we have an infinite number of these, then these are very, very thin, infinitely thin, where this is a dr or a dx or something, right? Which denotes this equals 0, but it's in the limit as some side goes to the 0. Okay, so, or it's goes to 0, however how you want to say it. So what does this mean? Well, let's say, okay, remember this picture here? I'm going to redraw it like this. If I redraw it like that, this is tau r, and this is r. So what's the area? 1/2. Why 1/2? Because, we've only got the shaded in areas, right? 1/2 tau r r. That is a very direct perception, I would say, of the slant area. Extremely direct perception. 1/2 tau r r. I mean, that's really good. I have to say. Another way to say it is 1/2 that little circumference on the bottom times the slant height. You want to use L. Different ways to see it. Now, what happens when the slant height equals the radius of the base of the cone?
It becomes circle, maybe.
It becomes a circle. And what's the area? 1/2 tau r r. Which is pi r squared. You guys aren't getting as much a kick out of this as I am.
Wait, so you basically took the cone and you're saying like, okay, we're gonna squeeze it down to infinitely to 0, and then it's basically a circle.
Exactly. The slant height becomes the area of
Okay.
the.
Tran caught that quick. I didn't catch that. I was trying to envision that, but yeah, and then like the opposite, what would happen if you went to straight infinity?
Okay.
know?
Well, if you did that, you would get an infinite. Right? But that's a good question. You should definitely ask both ways. Okay. But wait, what's really fascinating about this though is it's 1/2 tau r r, which is pi r r, which is very much like pi r squared. It's kind of like we took one of the r's in the r squared and assigned it to the other r. Now contemplate that for a second. Wait a second. It's like I could have said pi r squared, or I could have said pi r squared, but instead I said pi and a little r from each. Now, if you were to multiply pi r squared times pi r squared and square root it, you would actually get, you know what you guys would get? You'd get pi r r. And this is called the geometric mean. So it's actually the geometric mean of the big circle and the little circle. Am I right about that? But just so you know, I'm just coming up with this right off the top of my head right now. Just so you know, right? I try not to prep for these sessions because the whole point is not to prep.
If there is a relation between small and capital R, of course.
What was that?
If there is a relationship between small r and capital R,
If there's a
then
what
we can-
between them?
geometric progression.
Okay. So the slant area squared equals the area of the base times the area of the big circle, which doesn't really exist on the cone, but it's a part of the cone, right? I'm just pointing out some interesting things because that's a nice, to me, that's an elegance that is very satisfying. Everybody knows pi r squared, right? Imagine you talk to your students, Robert, about this again, and you said, well, you guys know pi r squared, right? Well, instead now half of the one r goes to that part of the circle and one r goes to that circle. It's still pi r squared, kind of, right? Right, it's like, but it's got 1 r from each circle. Pi r r. Or 1 over tau r r. It's good to try to see them all in all of them, all the different ways, right? Pi r r is kind of nice when you're saying, hey, it's like pi r squared, right? 1/2 tau r r is nice when you're looking at it like the comb of triangles, right? All right, and there you have it. Perception is first, description is second. So we perceived it, and we've now just described it in the language of mathematics. So, I mean, I guess you could apply it, but it's almost so easy. It's like, why would we even do it? You have an ice cream cone. It's 1 inch. Okay. And that's 3 inches. Okay. So what's the area of it? 3 pi inches squared. Okay. Right. Yeah, I mean, we can apply this. And I've got an ice cream cone. Right. This is 3 inches. This is 1 inch. What's the area of the waffle stuff? Right. You might say, okay, it's 1 times 3 times pi. Right. It's pretty straightforward. And you're like, well, what if it's a very flat ice cream cone like this? Well, then these basically become the same, and it becomes 1 times 1 times pi. Or we can have Robert's ice cream cone, which goes on for infinity. Then we got infinity times 1 times pi. Robert's got a very decadent ice cream cone right there. So, all right. Is there anything else we can do with this? I think it's important to recognize the Gaussian curvature is 0. And maybe you guys want to study Gaussian curvature. Something I've been actually thinking about a lot lately. Basically, if you have a surface, at some point on that surface, there's a Gaussian curvature. So for a sphere, the Gaussian curvature is uniform. It's the same everywhere. For a cone and a cylinder, it's uniform, the same everywhere. It's 0 everywhere. For a sphere, it's actually not 0 everywhere. It's the curvature squared. What is curvature? Curvature is 1 over radius. So it's kind of, yeah. So if this is the radius, the smaller the radius, the tighter the curvature. If the radius becomes infinity, what happens to the curvature? It becomes 0. It turns into a straight line. It's a circle that encompasses the whole universe because it's a straight line. Right? Fun concept, right? Okay. If the radius becomes 0, it's a little point that wraps around itself so tightly, it's got infinite curvature. So in a Gaussian surface, if you picked some point, say here's a top view of the surface, if we pick some point on the surface, there'll be a biggest curvature and a littlest curvature. And let's say the biggest curvature goes along this direction and the littlest curvature goes along some other arbitrary direction. The Gaussian curvature is the product of those two numbers. And if one of the circles faces down underneath, then it becomes a negative Gaussian curvature, like a saddle, you know, a saddle shape. It's like this way and then this way.
That's my favorite graph.
Yeah?
Saddle graph. Yeah.
Nice, nice. Okay, so saddle has negative Gaussian curvature, and that's kind of like what it's known for. Or one of the things it's known for. Okay, so now in a sphere, everywhere on the sphere, the two circles are the whole sphere, right? So that's a uniform Gaussian curvature. So what else can I tell you? So Gaussian curvature is it's important to know when the Gaussian curvature is 0. And in this case, it is. And that's called a developable surface. You can like unravel it.
So when the radius goes to infinity, the Gaussian surface becomes 0, yes?
Oh, when the radius goes to infinity. Yes, when the radius goes to infinity, the curvature goes to 0 and you get a plane.
Yes. The same goes for the circle. When the radius is going towards infinity, we get a straight line. So that's why we can manipulate it in terms of geometrical shape like triangles and rectangles.
I don't think that's the reason why, right? Because you couldn't. It's just because it's equidistant, right? So, I mean, could you do that with an ellipse? I mean, you could probably do it with an ellipse too, but you wouldn't have a constant radius, right? So then you would have to consider how those triangles are changing heights.
When you were talking about the direct perception of area of circle, in that also the base of that rectangle that we are forming, it is not a straight line actually, yes? There is a little curvature to it. Although we call it a rectangle, but
yeah, you have to take it to infinity, exactly. But that doesn't mean we're making the circles straight. So the way you were thinking about it, I'm not sure if that doesn't seem to apply to me.
no, I am trying to connect that while describing the perception of slant area, you were talking that some figures could be contemplated as Gaussian surface and we can
Yeah, I think
manipulate and
where
some
it's
cannot be.
relevant isn't in the fact that the triangles go like that. Well, that's more of a calculus concept. Where it's relevant is that we can unravel the cone and have it be a part of a circle, which is flat. So the cone surface is actually a flat surface, a sector, turned into a three-dimensional surface, which means that still has a Gaussian curvature of 0. That's my point.
Okay. In terms of plane, its curvature now becomes 0.
In terms of what?
Plane.
Yeah, because it's a plane. It's basically in that kind of mathematics, we kind of think of a cone as a plane.
Yes.
And we actually think of a cone as a plane and a cylinder as a plane. When we're, I mean, obviously it's different than a plane, but if we're thinking about it in terms of the curvature of the surface, then it's a plane. So yeah, they're all planes. The surfaces that are flat.
And in this slant area of cone only, the first and the obvious uh, obvious what to say?
Correct,
Obvious
Corinne,
thing
we gotta wrap up. I want to make sure we're done on time. So
Okay.
text me if you want to share something. Because we got 5 minutes left and that's when we have to stop. So thank you for sharing though. I love that, Corinne. Appreciate it. You're awesome, Corinne. Thank you. Um so let's see. Let me share my music. Listen to a song. All right. Now notice as soon as you close your eyes, It is the experience of cones and surfaces and things. Namaste, everybody. Wonderful. And tomorrow is our meditation class. We're doing the 4 paths of yoga. And